So last time we finished just by showing you an example of an astrophysical example of synchrotron emission. Uh, Please, could you, any one of you, mute the microphone? I can hear some noise in the background. So unless, if you have some technical problems, please let me know. Unless, please mute yourself. So, as I was saying, I'm still seeing I'm still hearing some noise. So please make sure you are muted.
It was my fault.
Okay, no problem.
Yes, sorry.
It's okay. So we are seeing the very last picture we've seen last time, which is an image in the radio band around 400 megahertz of our own galaxy. So the plane that you see is the galactic plane. And in particular, the bluish line is just the synchrotron emission to what? Well, this emission is around, you know, the frequency. That's the radio frequency I just told you. And we know from other sources of information that our galaxy, the magnetic field filling our galaxy is around of the order of 1 microgauss, which is typical of the magnetic field that we also measure in other galaxies. So you know the frequency. We know that this is synchrotron emission from positrons, and you will see why they are relativistic positrons. By the way, the source of these positrons is not clearly well defined. So this is also another problem, an open problem in astrophysics. Nevertheless, you know the critical frequency. You remember from the last time, the critical frequency is the frequency at which most of the synchrotron power is emitted, which depends on which scales is with gamma square. With gamma is the Lorentz factor of the electron or of the charged particle, and also with the magnetic field. So you know the magnetic field, you know the critical frequency, so you can measure gamma straight away. And if you carry out this exercise, sometimes I don't show you explicitly the calculations, but whenever you realize from my comments and from that you have all the information to make sure to check yourself the results that I'm seeing, that's something that I strongly advise you to do. So just to make sure that you are in control of things, make sure that with a critical frequency around 400 megahertz, with a magnetic field of 1 microgauss, indeed, you can estimate the Lorentz factor in this case of the positrons, and it turns out to be of the order of 10 to 4. So these are ultra-relativistic positrons. So this is also a powerful way, an independent way to measure the energy. And so as a consequence, you can try to investigate the source of who's responsible for these positrons, in particular, who's responsible for accelerating them to these energies. Another galactic object, which is really one of the most studied in our own galaxy, is the so-called Crab Nebula. The Crab Nebula is essentially what is left over from a supernova explosions that took place exactly in year 1054 after Christ. We know that from, of course, historic recordings from many different places all over the world, also in Europe, in China, in many places. So what we see now today is just, you see here, for example, this is a composite image from both optical and X-rays. The bluish one light is just X-rays. So not only do you see essentially the leftover object, the compact object, which is a pulsar, which is spinning, roughly speaking, 30 times per second. And we know from stellar theory that this is indeed what is to be expected when the progenitor mass is within a given range. And but you see all the ejecta here, which are expanding through the interstellar medium. So they get hot. We will study this kind of process when we will be studying shocks. So what shock waves do. But in this case, what is interesting is the fact that this object, so the central object, the pulsar, is powering through a so-called pulsar wind, a so-called synchrotron nebula. So you have essentially, you can look at the central object as an engine capable of, which keeps accelerating particles to ultra-relativistic energies. There's also magnetic field. So you immediately see that you have ultra-relativistic particles within magnetic field, so you're expected to see synchrotron radiation. And indeed, for example, it is possible to see, to measure not only synchrotron radiation, for example, here in this image in the optical range, but also you can measure also polarization, because as we will see today, one of the distinctive features of synchrotron radiation is a relatively high degree of polarization, linear polarization. So by combining these two pieces of information, you see that this is also another fair example of synchrotron radiation, in this case in the optical band. So let's be more quantitative. Here for the typical magnetic field within the Crab Nebula, the synchrotron nebula is around 510 to minus 4 Gauss. This information comes from different considerations about equipartitions of energy between magnetic field and charged particles, but this is again something which we'll touch more in detail in the next classes. So let's just assume that we have some channel through which we can estimate the magnetic field. We take this image, and we know from the spectrum that we will see in a moment, from the Brooklyn spectrum of this astrophysical object, that indeed the radiation that you see in this picture, and which is in the optical range, as I say, is synchrotron emission. So you can again estimate the Lorentz factor of the electron, which are responsible, which emit synchrotron and at this wavelength. We will see, getting back to the Crab Nebula, that indeed there's a lot of electrons with a range of very large range of energies, and so very large range of Lorentz factors. And we will see that each of them, of course, depending on the Lorentz factor, contributes their corresponding critical frequency is different. So you will see their synchrotron emission at different frequencies. In this case, we focus on the optical band. So we wonder, what's the Lorentz factor of the electrons which are responsible for the synchrotron radiation that we observe in the optical band? Well, first of all, let's calculate the so-called cyclotron. You just need the magnetic field. So you just, of course, E is the electron's charge. So the cyclotron frequency is just some kilohertz. You see 1.4 10 to 1.4 kilohertz. Now, but we indeed observe this radiation around in the optical, a typical frequency range that you can assume is 5, 10 to 14 hertz. So if we interpret this as the critical frequency, well, the critical frequency is neglecting the 3/2 factor. This is not the point and the sign of the pitch angle. But there's an order of magnitude estimate. You immediately see that the synchrotron or critical frequency is gamma squared times the cyclotron frequency. So if you work out just the ratio between these two frequencies, you have an estimate, the square root of the ratio, of course, you have an estimate of the gamma. So, and it's immediate to see also by high, essentially, that you end up with a Lorentz factor close to 10 to 6. So again, the astrophysical question that rising is, of course, how is concerns the process which is capable. So what's going on there? How can this source be capable of accelerating electrons to such high Lorentz factors, to such high energies? We will see that this object is capable of doing even of accelerating even to much larger energies. And yes, this is a spectrum of the Crab Nebula, a very broadband spectrum, because if you look in the bottom x-axis, you see the energy of radiation in units of electron volts, while in the top x-axis, you see the very same information expressed in hertz. So, for example, you see here from the radio band, this is the optical. This is the optical range in which we are considering, and this is also another component at very high energies. You see, for example, this is just in the gamma rays, while this component is in well above in the TeV range. So this is a very broadband spectrum. By the way, mind that what you see shown here is not intensity. Here S is not the source function. S is just the flux density. But if you pay attention, what you see plotted here on the y-axis is not flux density, S, but it's nu times flux density. This is usually adopted as a way of showing the spectra of sources in astrophysics, because, well, I can prove it mathematically, but this I don't want to do it now, because essentially it's a way of seeing the so-called nu F nu spectrum, where F nu is usually the flux density. So the nu F nu spectrum, if you look at, in particular, if you look at the peak of the nu F nu spectrum, and this is indeed a plot of the nu F nu spectrum, the peak tells you where most of the energy is released in terms of decades. Essentially, when you want to compare the energy released per unit decade, so in a logarithmic sense, the nu F nu plot, so plots like this one, are immediately telling you graphically the answer. So, for example, here you see that the slope, again, this is a log-log plot, so the slope means the index of a power law. So you see here the slope is negative, it's close to minus 1/3. But if it is negative, in the case of just the flux density, you should see some decreasing function. So it is increasing because it has been multiplied by an extra nu. So that explains just the. And by the way, given that this value is close to 1/3, 1/3 should make sense to you, because 1/3, if you remember, is the low frequency region. If you consider one single electron with a given Lorentz factor, remember that well below the critical frequency, the spectrum of synchrotron radiation due to one single electron behaves like 1/3 power law. So this is nothing but that very thing. So particularly when you are very at very low frequency, but still in this case still above the self-absorption frequency. So you are still in the optically thin regime, but yet here you are just sensitive to, you are far below the critical frequencies of the electrons. So that's the part of the spectrum that you are seeing. Well, in this part here, this is indeed the power law that you would expect, and that we've seen last time, that you would expect from a power law distribution of electrons. So depending on the frequency at which you look, and in the previous slide, I just make the example of synchrotron radiation around the optical range, which is here. Here, this is the optical. So this is the part of the synchrotron spectrum due to a power law distribution. So you measure the index, which is here around 1.1. So you can also estimate the P. So the value which tells you about the distribution of the energy of the population of electrons. But what we care here about is the fact that indeed the spectrum shows evidence that the radiation that we measure around in the optical range is indeed synchrotron emission. So as I showed you, the electron responsible for the emission here have Lorentz factor of up to 10 to 6. And we will see also, or then we will apply the same considerations also for the part here. And when we will be studying, probably in next class, the so-called inverse Compton effect, we will see that here this extremely energetic part of the spectrum is due to a completely different radiative process. This is synchrotron, this is something else. So the Crab Nebula is a fantastic lab to see in place many different radiative processes. The astrophysical object, as I said, is a relatively young object in astrophysical standards, which keeps accelerating particles to extremely high energies. And you will see why I say it keeps accelerating. Another example is just if you look, for example, in the radio bands, some galaxies, particularly some elliptical galaxies, you'll see this kind of lobes which are very bright in the radio band. And again, the result of the summation is just synchrotron emission, because as a matter of fact, in the center of these galaxies, there are two powerful jets in two opposites, just moving in two opposite directions. Jet of ultra-relativistic matter expanding. In particular, you have a lot of electrons here accelerated, which are at some point within the magnetic field region, of course, they inevitably emit synchrotron radiation. And again, in this case, considering the combination of the value of the magnetic field and the Lorentz factor of the electrons, you immediately see the corresponding critical frequency, so also called synchrotron frequency. So the frequency at which you expect most of the synchrotron power to be emitted lies in the radio band. So if you just, this is a typical image in radio bands, as I said. You see there's two very bright lobes, which are just due to synchrotron radiation. So very energetic particles, in this case, electrons which are being accelerated by the inner engine lying within the galaxy center, and at some point they emit synchrotron emission. So it's important to define at this point the so-called cooling time. What is that? Well, if you think you have energetic particles, but you have also a mechanism which dissipates their energy. So you immediately realize you have an energy reservoir, which is for a given particle, which is its total energy available, and the mechanism which, if it keeps working, at some point it dissipates, it uses up the energy. So it makes sense to wonder how long does this can last. And a very rough estimate, of course, if you think of the process, as long as the particle loses energy because of synchrotron radiation, of course, its Lorentz factor decreases. But by decreasing the Lorentz factor, as a matter of fact, as a consequence, also the power, the synchrotron power, which I remind you scales with gamma square, also decreases as a consequence. So to make a detailed calculations, one should, in principle, solve a differential equations, because both energy and energy range at which energy is consumed, they change with time. But just in order to have an order of magnitude estimate, you can just work out the so-called cooling time, so the time it takes for the particle to cool down, so to lose most of its energy, entirely due to synchrotron radiation. So assuming that synchrotron is the dominant process through which the particle is losing energy. So you can just work it out just by simply dividing the available energy reservoir, so the energy of the particle, over the average power due to synchrotron, just like that. So energy over energy per unit time, of course, is a time. So let's see in detail concerning, and this is a very general. So whenever you have a process, a radiative process, which is dissipating the energy of a particle, you can always associate a cooling time. Just divide the total energy over the power of the corresponding radiative process. So if we carry out this exercise in the specific case of synchrotron emission, which is exactly what we are doing now, so the total energy of the particle, gamma mc squared, over here I put just the total power, the average power in the case of an isotropic population. Here, the point you see, if you pay attention to the scaling with gamma, you immediately see that indeed, the higher the gamma, the correspondingly higher will be the energy. So in principle, the energy reservoir that you can use. But the power scales in a stronger way with gamma squared. So as a result, for example, let's replace the numerical values in the case of electrons. So by just taking all these values, just leaving the Lorentz factor and the magnetic field intensity in the Gauss system, you see essentially that overall, the higher the Lorentz factor, so the more energetic the particle, and the shorter the cooling time. So if I had to make a comparison, it works in a qualitatively similar way to the lifetime of main sequence stars. If you think the more massive a star, the more fuel you have in principle. But you know that during the main sequence phase, the luminosity scales with a strong power of mass, 3, 4, depending, 3, let's assume 3. So that's the reason why massive stars live much shorter than less massive stars. So here is the dependence is different, but qualitative point of view, the mechanism is the same. The more energetic the particle, so in principle, the more energy you can use, but the synchrotron power is scaling with gamma squared. It means that the more energetic the particle, the shorter the cooling time. And this is very important to take into account. In particular, there is a 1 over gamma dependence. So it's nice to see some example. In this formula here, the only quantity, B0, is the magnetic field meant to be in Gauss unit, in Gauss. So let's see. Okay, this is instead of seconds in years. I remind you, 1 year is 3.1 10 to 7 seconds. So this is also useful to remember to make calculations. And so let's see a few examples, typical examples in astrophysics. So if you consider a so-called supermassive black hole, these are objects which by now we know essentially every galaxy hosts one of these beasts. For example, our own galaxy, the Milky Way, hosts a black hole which has a mass of about 4 million solar masses, which is one of the least massive in the big family of supermassive black holes. I'm sure all of you have seen the historic image of the black hole horizon of the supermassive black hole of M87, which is a galaxy relatively nearby galaxies, which they were able to calculate to have a very accurate angular resolution in the radio using the very long baseline interferometry. But anyway, what really made a breakthrough image was just the capability of seeing the horizon for the first time of a black hole. In that case, the black hole has the mass of the order of 10 to 9. So almost a factor of 9, almost a factor of 1,000 with respect to more massive than our own black hole, than the black hole that lives within the center of our galaxy. So anyway, just to take an example of these beasts, we know that they're in their surroundings. The typical magnetic field can be as high as 10 to 3 Gauss. We also know that the Lorentz factor of particles can be of the order of 1,000. So you immediately see by replacing these value into the cooling time formula that these electrons cool very fast within a matter of seconds. Well, another example, if you take radio-loud quasars, so quasars which are very bright in the radio band, again, these are typical values. So in this case, the magnetic field is much weaker, 10 to minus 5. Same comparable Lorentz factor as before. And you see that the cooling time is completely different, also because of the square dependence on the magnetic field. So in this case, of the order of over a few 100 million years. To make an example which is closer to us, so staying just in the Milky Way, as I said, as I already showed you, the example of the positrons that I made in a couple of slides ago. As I said, the typical magnetic field is of the order of the micro-Gauss, and we've seen that the Lorentz factor of these particles can be as high as around 10 to 5. So you can wonder, what's the average lifetime of these electrons, of these positrons that are responsible for the summation? Well, again, here at 246 actually doesn't make really sense. You can just round the number of 250 just in any case. In any case, this is just an order of magnitude estimate. So you see that these positrons in this case can live up for a very long time. Well, again, just getting back to the example of the electrons which are responsible for synchrotron emission that we observe in the optical band from the Crab Nebula. Again, the intensity of the magnetic field can be of the order of 10 to minus 5, 10 to minus 4 Gauss. The Lorentz factor, we see that it's almost 10 to 6. So you see that the synchrotron emission cooling time for these electrons is just little more than 100 years. Now, that if you think carefully of what I told you before about the age of this object, this is about to celebrate 1,000 years age, because, as I said, it exploded in 1054. So in kind of 34 years, it will celebrate its 1000th birthday. But now the point is, if you look at the cooling time of these electrons that we keep observing every day, it means that should you assume that these particles were accelerated in the aftermath of the explosion, and then the engine essentially stopped or got really quiet, you wouldn't be able to explain this synchrotron emission, because you see that the lifetime, the cooling time of these electrons, they use up all their energy in little more than 100 years. But the object is much older, is 1,000 years. So the fact that you keep observing these electrons emitting synchrotron radiation, despite their much shorter cooling time, it means that they have been accelerated recently. So this is compelling evidence. This is direct evidence that the Crab Nebula is keeping, centuries after the explosion, keeps accelerating electrons, in this case, to very high energies, even today. So this is really important. You see the role of, you see the importance of estimating also the cooling time of this process. So this is telling us something very important about the way the compact object, the leftover of this supernova explosion, keeps working. And getting to a much closer example, so if you consider the Earth magnetosphere, in this case, the typical magnetic field is a fraction of Gauss, and the Lorentz factor in this case can be of the order of 100. And you see that in this case, the corresponding cooling times of the other few years. This is just to provide you with a plethora of examples, and also with the idea that synchrotron emission indeed can be ubiquitous, just because magnetic fields are, as well as energetic electrons are as well, depending then on the energy range that you have in mind. You'll select different things. I made one statement right before, and probably also last time. I said one of the distinctive properties of synchrotron radiation is the relatively high degree of polarization. Now let's go to somehow details. I'm not going to go through every single calculations because that would take us too far or too long, and that's not the point I want to make. But at least I want to show you the essence of the calculations. So let's suppose here we are looking at one single electron at one single moment. Let's suppose that at the initial time the electron lies within the origin of this Cartesian system reference frame. So in particular, the velocity at 0 time, when the electron is just right in the origin, is directed along the x-axis. So and you see this curved line is just a portion of the trajectory of the electron. Okay, so the trajectory in this point lies on the xy plane, and the acceleration is all the time perpendicular. So in this case, we assume the acceleration is along the y-axis, directed this way. Okay. We also assume that the magnetic field lines, which here I colored with red, lies in the xz plane. Now, if you work out the Lorentz factor, the Lorentz force, of course, v vector b, you see that this is something lying along the y-axis. The direction is due to, it already takes into account, of course, the negative charge of the electron. And this direction here with the unity vector n is nothing but the generic direction of the observer. So this is our I. If we receive radiation, if we are looking at this electron just from this direction, n is just pointing towards us. And also n lies within the xz plane, so this plane. This is the moment at which essentially we get the peak of the radiation, depending emitted by the electron through synchrotron radiation. So if you remember this angle, which is theta angle, which is the angle between the direction of observations and the velocity of the electron, here is shown as a relatively large angle. But you remember this is an ultra-relativistic electron, so the relativistic beaming is at play, which means that most of its energy is emitted within a cone with 1/gamma aperture. So indeed, you should imagine that, as a matter of fact, this radiation becomes important when gamma is very small, when theta, sorry, is very small. So when the direction of observation, when the line of sight is relatively close to the velocity. So here we define, so you're looking at here, you define two different directions along which you imagine you can project the electric field that you measure of the electromagnetic wave that you receive. This unity vector is called epsilon perpendicular, and this is epsilon parallel. Parallel and perpendicular to what? Well, to the magnetic field projection from your point of view. So again, if you pay attention to what I said the magnetic field lies in the xz plane as well as the vector n. So this guy here is perpendicular because it lies along the y-axis, so it's perpendicular to the magnetic field line, while in this case, this guy here is parallel to the projection of B from your point of view. So, okay, this just summarizes what I just said. So Yes, indeed, epsilon parallel can be simply obtained by through the vector product and vector epsilon perpendicular. So, and indeed, of course, the two perpendicular, parallel, and the line of sight makes a right-hand triad. The goal, at least we will, as I said, we will not go through every single detail because it's a quite complicated proof that you can have a look at in its entirety if you take the Rybicki-Leitman. So I will give you the more precise references. But here I just want to catch, just to take the essence of the proof. The idea is to work out, to project the electric field. So what one ideally should do is take the formula which gives you the radiation field, so the electric field of the radiation component. And if you remember, there's an n vector b dot. So you have to n vector a, which will be something like n vector a, which will be something like this, and then n vector a, and you see, and you have the direction of the electric field. The idea is to project this electric field on both perpendicular and both parallel projections, and you work out the corresponding intensity along the perpendicular direction. Perpendicular and parallel, I keep saying, with respect to, it's meant to be with respect to the magnetic field line projection. So the idea is you work out, in principle, the electric field, and you project along the perpendicular component. The one along the parallel component, of course, you have to work out, taking into account the retarded times, all the stuff that we commented several times. And then you work out the corresponding intensities separately. Why this? Because the goal is to measure the linear polarization, or the kind of polarization, whatever it's going to be. And to do that, of course, you have to realize that you have to monitor, to sample, to study how the intensity depends on direction. That's the essence of what we are aiming at. And yes, okay, this is just the more detailed reference. So if you want to see the full details of this proof, just the Rybicki-Leitman section 6.4. What you come up with. So I just show you the result immediately. That's why. But I wanted you to at least to catch the essence of the. Then this, as I said, you have to battle our way up some algebra in order to get this. But I mean, it's not worth it for us to get through it. So you end up with this. You see, power per unit frequency per unit solid angle. In two different, projected along the two different directions that I was telling you, the perpendicular one and the parallel one. Here there's a few quantities that needs to be defined. So in particular, there's a quantity which is theta gamma. Theta gamma is just something which encodes the dependence on the well, for a fixed electrons with a fixed Lorentz factor. It just shows you the dependence on theta, because in principle, I already told you last time that you see just a pulse when the line of view lies within the relativistic beaming cone of the particle, and this just happens for a relatively short time interval. But in principle, of course, emission is to any possible direction. So to carry out calculations, you have to consider emission from the electron throughout the entire orbit, not just, even if we know that, as a matter of fact, most of its energy will be flashed to you in that very short time interval. So here, theta gamma is just nothing but this guy here. And it's also worth seeing you see the combination, the dependence on theta gets through a combined product of gamma times theta. And you can see this product as a ratio between two angles, theta over 1 over gamma. So it's the angle matters as a unit of the beaming angle. So you should look at this product as a ratio between angles. The generic theta angle and the angle which gives you the measure. And the angle which gives you the measure is 1/gamma, relativistic beaming. And here you have another quantity, which is eta. Eta is defined as this guy. Here, A, mind that A, I didn't write it, but A is this guy here. So is the curvature radius, not to be confused with acceleration. So it's just the curvature radius. So something that I already, the same notation that I adopted in the last class. And due to the fact that, as a matter of fact, gamma theta is very small when you have most of the contribution, for the very reason that I just told you. This guy, so when theta is close to 0, it means that this guy is essentially 1, and it's possible, it's easy to see that in when you approximate theta to 0, so this guy is 1. And if you remember the definition of the critical frequency, 3/2 omega b, where omega b is the cyclotron, is the gyration frequency, sine theta, sine alpha, sorry, where alpha is the pitch angle. You see that you have this guy here right away if you use one of the formulae that we obtained for the curvature radius as a function of the pitch angle in omega b. So again, eta is a function of just the generic frequency at which you study the electromagnetic emission over the critical frequency. So again, the dependence on omega, on frequency, always passes through a ratio, so in units of critical frequency. So again, this is also very important. And k is just a modified Bessel function, 1/2 or 3, 1/3 order, whatever it is. So integrating, as I said, the contribution comes from a relatively small portion of the trajectory, but you have to consider the entire orbit to work out the full calculations. So again, here you have to go through some mathematical tricks that are described in the Rayleigh Lightman. I'm not going to spend any comment on that. But you end up with this relatively simple spectrum. So you see, we keep separate again the intensity or energy per unit frequency, the specific intensity, for the two polarization modes. And you see that there is a different, you can express using these two different functions, one of which was already introduced by me when I described the spectrum of synchrotron radiation. Remember this capital F, which describes the total spectrum, no matter about the polarization direction. This function here, again, as a function of the integral of this modified Bessel function. G is the new one. It's a slightly different definition. What's the impact? Yes, well, where x, of course, is meant to be the ratio, the frequency in units of critical frequency. Now, the very same trick that we used last time when we wanted to study the total spectrum of synchrotron radiation, in that case, we didn't care about the polarization. So the only difference here is that we keep separate the two polarization modes. So we just do the very same trick. We divide, we calculate the average power by dividing time average power by dividing by the orbital period, which again depends on the gyration frequency. The gyration frequency is QB/gamma MC. So just this guy here. So if you replace, if you divide those powers by t, which means multiplying by the reciprocal of this guy, so you gain an extra factor of q to the second power becomes q cube, and then you gain an extra factor of b, and then gamma, you see, just cancels out, and you are left with this guy here. This coefficient is the same as for both polarization modes, and if you remember, it's exactly the same coefficient that we ended up with when we calculated the total power the total synchrotron power of one electron. Now, the total power is, of course, the sum of the two independent polarization modes. So it's nothing but that. But if you look at now the formula here, you immediately see that we indeed recover the formula that we already obtained, that we already commented. So we know very well what this looks like. I remind you, F in the two asymptotic regime behaves like a power law of 1/3 slope for very low frequency, and then there is a square root of the frequency times a negative exponential at very high frequency. Very low, very high frequency. It means all the time compared to the critical frequency. Okay, so the additional information that we have now with respect to is that we split the total power between the two different polarization modes. So we immediately see that this is not equal. They are different. In particular, it goes without saying that the perpendicular component is stronger, is more intense. You immediately see that because G is a positive quantity. So let's have a look. If one plots the two powers, so the two spectra, as a function of frequency, in particular here, given that, getting back, you see the only dependence on frequency is through the F and G functions, but F and G just depend on the ratio between the generic frequency and the critical frequency. So instead of, it's much more meaningful to use as the independent variable the ratio, so the frequency in units of critical frequency, what we call just X. So you see that the intensity, the two modes, so the solid line, as I wrote here, is just the perpendicular the intensity along the perpendicular component, and the dashed line is just the one of the parallel. You immediately see that indeed you have a stronger intensity along the perpendicular one rather than in the parallel. In particular, if you work out the linear polarization degree, which I remind you in this case, if you remind also how we define the linear polarization degree. For example, if you think of the ellipse axis of the polarization base that we've seen when we talked about polarization, it's immediate to see that essentially the linear polarization degree is just find the two perpendicular directions along which you have respectively the strongest and the weakest intensity, and this is just their difference over their sum, just like that. So this is just equivalent to the definition of linear polarization degree that we defined at the time. So with capital Pi as a function of frequency, indeed, because we see that the two intensity are indeed functions of frequency. You see that the polarization degree is really high, relatively high, from 50% almost up to, depending on frequency, to very large, close to 1 at least, depending on the, as I said, on the frequency that you are looking at. And indeed, just by replacing what we've seen is just the ratio between the G function over the F function. Now, let's have a look at the way it works. Well, again, the figure here shows you so if you remember, we defined this as the so-called velocity cone. So you have the magnetic field lines, which are shown here as horizontal lines. So the magnetic field lines are these here. And this is the pitch angle. So the angle between the velocity of the electrons and the magnetic field lines. So it means that the velocity of the electrons just keeps rotating line within the surface of this cone, okay, because the angle is constantly alpha. So you imagine you have the velocity of the electron, which is just spinning around on the surface on this cone. But again, here, if you assume that gamma is the Lorentz factor, so 1/gamma is a relatively small angle, because we are talking about ultra-relativistic particles, electrons. So it means that, if you remember again, because of relativistic meaning, most of the radiation, given that the velocity is a vector in this case here, but then of course it rotates, keeping an angle alpha with respect to the horizontal lines. So let's suppose the velocity at some moment is right here. So you see that the radiation will be emitted within 1/gamma angle. So it means that among all the possible lines of sight through which you are observing the electron, most of the radiation will be emitted along these line of sight. So the line of sight that get through this shaded region. So close to the border, to the boundaries of the velocity cones. Well, in principle, at any direction, but most of, as a matter of fact, because of relativistic beaming, most of the radiation will be observed only when the line of sight lies within this relatively narrow border around the velocity cone. So imagine you are an observer. Imagine you are projecting the electric field that you measure within the two directions, the perpendicular one and the parallel. Perpendicular and parallel to what? Well, to the projection of the magnetic field lines onto your plane. So let's assume probably from the geometric point of view, the easiest case. Let's suppose you are just right on the line of sight is parallel to the magnetic field lines. In this case, what you see, due to a given electron with this pitch angle, you will see a circular polarization, also for symmetry reasons. You have to remember that if you imagine the acceleration felt by the electron, the acceleration is something constantly perpendicular both to velocity and to the magnetic field lines. So it means that, as a matter of fact, if you imagine as the electron moves, the acceleration vector felt by the electron is something which rotates. And by rotating, if you remember, if you look at the formula of the radiation field, which determines the direction of the electric field that you measure, rotate as well as a consequence. So you see an electric field which is rotating all the time according to a circular polarization, because there is full symmetry on the axis. So every single position is completely symmetric with respect to any other. So that implies circular polarizations. But based on what I just said a couple of minutes ago, if your line of sight lie relatively far from the shaded regions here, it means that you will receive a very small amount of radiation because you are out of this region, and this region is where the line of sight collects most of the radiation emitted by the electron. So you will, in principle, receive some radiation here, and you will see some circular polarization. But the amount, as a matter of fact, the amount of radiation that you will receive is very small, very weak. So that's not you're not gonna get a significant amount of radiation if you look at this particular electron just lying on this line of sight. So you have to look here. Now here you have three different cases, depending on whether you are slightly within towards the inner part. So let's suppose you are here, but not right on the line of sight doesn't really lie exactly on the velocity cone surface, just slightly inward. Okay, so the result is that you will see an elliptical polarization going through this way. While if the line of sight lies exactly on the velocity cone, as a matter of fact, looking at this plot here, this is imagine this is projected on this plane, okay? So when you are here, you see an elliptical polarization with the axis with respect to the perpendicular direction, which is higher than with respect to the parallel one. If you lie exactly here, so at some point the velocity will point exactly towards you, the velocity of the electron at some point will point exactly towards you. You will see no intensity along the parallel component. You will see just a linear polarization along the perpendicular one. While if the line of sight lies slightly outward with respect to the velocity cone, you will still see an elliptical polarization, again with the perpendicular direction stronger than the parallel one, but with the opposite sense of polarization. Okay. So this is important to note, and one can see more in detail why all this. You have to imagine that, as I said, imagine that the velocity of the electron just keeps rotating along the velocity cone, on the surface of the velocity cone. Why this is important? Well, because when you receive, imagine that you have, of course, this is just the case of one single electron with one specific pitch angle. But imagine you have a population, in a realistic case, you have a population of electrons. Let's suppose all of them having the same Lorentz factor, but with any possible direction of their velocity with respect to the magnetic field. So it means that if you lie here in one of these here, it means that you will receive most of radiation from electrons with not just that precise value for alpha, but also for other values of alpha which are close to it. So you will receive within an angle 1 over gamma the contribution of alpha. I would say alpha plus 1 over gamma minus 1 over gamma. All of them will be contributing. So as a matter of fact, you will see this, the electric field due to electrons all together, with both electrons lying on this side and also the others lying on this side. So you have to somehow imagine that you sum up all these cases together with equal weight in general. You have no reason to think that you have more electrons of one kind with respect to the other. You have, unless you have a strong reason to make assumptions on the distribution of the pitch angles. So it means that if you sum up electric fields elliptically polarized, behaving this way and this way, you see that the two contributions just cancel out, and what you see is just this guy here. The time average of the electric field is just linear polarization. So, and yes, this is essentially what I told you. So this is just the same picture seen from a different point of view, if you want. So I just imagined here the generic observer, the magnetic field line around which the electrons, the ultrarelativistic electrons, are orbiting and emitted synchrotron radiation. So imagine this is the plane perpendicular to the line of sight onto which you project the electric field. So you will identify the so-called parallel, which is just the projection of the magnetic field lines, and as a consequence also the perpendicular one. So you measure the intensity along both directions, and we see that you would expect, as I said, for a population of electrons, so no more just one single electron. When you sum up the combination, the population of electrons with different, as I said, pitch angles, you end up with a linear polarization, because the parallel one just cancels out. And indeed, so just working out this the polarization degree, that's exactly what you end up. The interesting case, again, for the very reason I already told you when we were interested in calculating the resulting energy spectrum of synchrotron emission in the case of a population of electrons, I told you, well, unlike the Bremsstrahlung case, here the typical population of ultrarelativistic electrons that one finds in several astrophysical contexts is just a power distributed population. So again, I'm not going to say it in too much detail because I've already said that. But again, that means that you have a distribution function which describes how each Lorentz factor is probable. So in particular, they are distributed according to a power law whose index P describes the power law. And typical values, for example, are 2 or 3. For example, in the case of the Crab Nebula, should be around 3. And depends on the way they have been accelerated to that. And we will see some examples in the end of this course. How you can end up with such a populations of power law distributed population of charged particles. And this holds between, of course, two boundary values of gamma, a minimum 1, gamma 1, and a maximum 1, gamma 2. So now we wonder, should we have, instead of just considering, as I did so far, one single electron with one single gamma, or a population of electrons with different pitch angles, but all having the same gamma, if we allow gamma to have a range of values, for example, as in this case, in particular, assuming this distribution, so what is the resulting polarization properties of such a population? Well, if you remember, we already calculated the total power, the spectrum, which we found out is also a power law whose index is P minus 1 over 2. Now, having to carry out this guy here, what we are supposed to do is just to calculate the intensity, now keeping them separate of the two polarization modes, and we have to calculate them for the entire population. But if you work out, if you work out the integral, the very same integral that we did here, in this case, but in this case, of course, you have to consider the individual formulae for I perpendicular and I parallel. If you remember, the only difference is that one is F plus G and the other, and I parallel, is F minus G. So F plus G minus F minus G is twice G, and here you have twice F. So that's it essentially tells you the specific calculation of the polarization degree when intensity are weighted by the population of electrons. And in this case, again, I'm not going to show you the mathematical details. I'm just showing the results. The result is a mere function of P, of the index of the electron energy distribution. So this is the formula, famous formula, which gives you the linear polarization degree for a population of electrons distributed with a given electron index P. So this can be really relatively high, as I said. Let's have a look. If you replace typical values for P, as I said, for example, when you study so-called gamma ray bursts, that I'm not gonna talk about them. Well, I did just very briefly when I made an example of polarization. But if you want to know more about them, you have to attend my optional course on multi-messenger astrophysics. But nevertheless, or just as I said, in the case of supernovae, the shocks that you have in some supernovae, it just accelerate electrons with an index P of around 3. So this range is very typical of what you observe in astrophysics. And you see just the resulting, the corresponding polarization degree can be really high, more than 70%. So this is also a very important consequence, which combined with the knowledge that you can acquire on the spectrum, measuring also polarization can be an independent tool to constrain P, and also to understand exactly the mechanisms that is at play that is accelerating electrons in this case, and you can get a lot of information. You can gain insight into the astrophysical object, which is responsible for the acceleration of these particles, as well as the environment conditions. So, for example, the magnetic field. So, polarization degree is a really important means to probe the conditions, the surrounding environment, as well as the engine responsible for the acceleration of these particles. And this essentially exhausts everything I wanted to say about synchrotron radiation. In addition to that, there's also another typical mechanisms that we will see very important in astrophysics, which is called curvature radiation. What is that? Well, imagine you have, for example, here a neutron star, an object which has a strong magnetic field, and the magnetic field lines are somehow bent, of course, because in this case you have a given structure. In this case, the simplest possible structure for a magnetic field is just a dipole structure. But that's not the point. So let's focus on the magnetic field lines here close to the surface, okay? So you see that these magnetic field lines are somehow bent. They are curved. Now, you already know that if you have energetic electrons, and indeed here, this is a place where you have energetic electrons, you can have stronger synchrotron emission. But, and of course, you know everything about that. But let's suppose we focus now on the, and of course, synchrotron emission, you know that you have a critical frequency, which is this guy here, which is just a reminder again of what we already of what we know about that. So here there's a factor of 2 pi which is missing, because here is the frequency, not the angular frequency. Anyway, let's suppose you have a pitch angle which is very small. So very small, it means that the critical frequency is small, the power is also very small. Remember the sine square dependence. The smaller the pitch angle, the correspondingly smaller the power lost for synchrotron emission. So in the limit case, so of course the obvious case is when the velocity of the particle is exactly parallel to the magnetic field lines, in which you have no emission at all due to synchrotron. So, but let's suppose you don't have alpha 0, but for example alpha close to 0. Because alpha 0 is just one, you have very few. If you allow alpha to be close to 0, but not exactly 0, it means that the electron will lose a very small amount of energy due to synchrotron, because sine alpha is very small. And the result is that you see that the electron, nevertheless, is just the motion of the electron is helical motion around the magnetic field lines. But now look, if you overall consider the resulting trajectory of the electrons, you see that just because of the curved lines of the magnetic field, also as a consequence, the trajectory of electrons will be also curved. But you know very well that a curved trajectory means acceleration. And in particular, you know that the acceleration is always perpendicular to the trajectory at any point. Okay, and depends on, it is the velocity squared over the curvature radius. You know this from your very basic studies. So it means that here you have charged particles which are accelerating. They are accelerating because of the magnetic field, but not in the sense that we already explored in the synchrotron emission. In that case, the acceleration is perpendicular to the magnetic field lines. So even in the case, for example, of a uniform magnetic field, it's not relevant for the synchrotron emission the structure of the magnetic field lines. The only ingredient is just having magnetic fields. In this case, the acceleration I'm talking about, is the acceleration due to the curvature of the trajectory. But the curvature of the trajectory is due to the curved magnetic field lines. So the source of acceleration is completely different. And because of the, here you have electrons moving along a curved trajectory. And if they are ultra-relativistic electrons, so again, you end up having ultra-relativistic electrons moving along curved trajectories. So you have radiation. In this case, the radiation is called curvature radiations, because it's due to the curvature of the magnetic field line along which the electrons are moving. And so we will see that the most effective mechanisms, as I said, this holds as long as you consider particles whose pitch angles are close to zero. And this is necessary to make sure that synchrotron emission can be neglected with respect to the new emission. Or put it with different words, you have to consider those pitch angle values for which the acceleration due to the synchrotron radiation, connected with the synchrotron radiation, is negligible with respect to the acceleration due to the curvature itself of the magnetic field lines. Okay, so you have two different sources of acceleration. So when the pitch angle is close to zero, the acceleration due to the magnetic field line, regardless of the structure of the magnetic field line, just what we studied about synchrotron radiation, is negligible. So we have that electrons now, these particular electrons with pitch angle very small, with very small pitch angle, lose energy through a different mechanism. Yeah, they still lose energy because they are particles which are accelerated, and so charged accelerating particle, we do know very well they lose energy. And since we are talking about ultra-relativistic charged particles, they lose a lot of energy. But in this case, the dominant process responsible for the energy loss is not synchrotron radiation. It's completely different. It's something which accelerates particles through magnetic fields, but exploiting the curvature of the magnetic field lines. So it's different. You have to realize why it's completely different. Yes, this is just... So the acceleration connected with the curvature of the magnetic field lines, of course, is something, just imagine this is the trajectory of the electron. So it's a curved trajectory. So the acceleration is just pointing toward the center of the curvature circle. And it depends, it's just v squared over rho, if rho is the curvature radius, just like that. So, as I said, because they are just charged particle, accelerating charged particle, they have to radiate. And indeed, this is called curvature radiation just because of that. You have an extra adjective whenever this is the case, which is coherent. Well, we will see in a moment that when you don't have just one single particle on its own, but you have a bunch of particles. In particular, that they lie very close to one another. So a bunch of particles, in particular, whose size is negligible with respect to the wavelength of the emitting radiation, of the resulting radiation. When this is the case, all these particles behave like one single particle because they emit coherently. The electric field, which results from the sum of the individual electric fields of the radiation fields of every single particle, just they add up in phase, because it's essentially, as I said, well, you can neglect essentially the difference in retarded times. And so they behave, they're instead of, as I said, there is a constructive interference. So the electric field of all these particles sum up together. And so you remember it works like, it works like interference. When you have coherent emission, it means that electric field sum up in phase. But given that intensity scales with the electric field squared, it means that this can have a huge impact on the total power. And indeed, that's what we observe, and we refer to as coherent curvature radiation. So when many particles are bunched together and they emit together. I'll get back to it in a few slides. So let's see that. Let's now exploit all what we've been learning, or what we've learned about synchrotron emission, to study also the properties of curvature radiation. How? I just said that the two things are different, because in one case, the magnetic field itself is responsible for the acceleration, while in the other case, it's just the curvature of the magnetic field line structure. But it's not the magnetic field in the sense that in this case, in the case of curvature, the acceleration is not due to the Lorentz force. This is another way of putting it. While in the synchrotron radiation, indeed, acceleration is due to the Lorentz force. So you see the action, how the magnetic field comes into play, the role of magnetic field. Here, it's not due to that. There is no Lorentz force here. Well, the Lorentz force is very, very tiny, just because the velocity of the particle and the magnetic field lines are almost parallel. So the Lorentz force here can be neglected. So the acceleration is just due to the fact that the electron is just moving along a curved trajectory. Of course, the curved trajectory is the result of the structure of the magnetic field lines, which are bent. But you see, it's a completely different mechanism. Here you have something which makes the electron accelerate due to something else. It's not the Lorentz force. So let's suppose we have, I call here the curvature of the trajectory as ρ at some point. So the A is the acceleration vector of the electron. Now, to exploit the results, or what we've learned about the typical frequency, the power emitted, in the case of synchrotron radiation, we want to use those informations in this case. But I just said that we have no such magnetic field here at play. So no magnetic field whose Lorentz force is responsible for the acceleration. Well, the trick here is to imagine a so-called fictitious magnetic field, which I will call BF. I imagine I'm dealing with a magnetic field BF such that its corresponding Lorentz force is exactly responsible for the acceleration. So in this case, I see the acceleration, which is due, as I said, both to the velocity of the electron and the curvature radius. So I imagine, just as a trick, this is a mathematical trick or a physical trick, I don't know, but I imagine that this acceleration is due to a magnetic field. So a magnetic field which you can easily imagine this is perpendicular to the plane of the slide, and whose intensity is such that its corresponding Lorentz force gives exactly the acceleration that I want and that I already have. Why is this useful? Because then you can exploit all the results about synchrotron radiation using this fictitious magnetic field. And yes, indeed, the magnetic field, if you work out the Lorentz force, taking into account again that the electron is moving this way, and so taking into account, of course, of the negative charge of the electron, you will see that you need a magnetic field, a fictitious magnetic field working like that. Now, yes, like the magnetic field, the fictitious magnetic field has to be such that the resulting Lorentz force is exactly this guy here. So the orbital angular velocity is exactly what we called at the time in the case of the synchrotron. You remember this was the gyration frequency. Well, now this is just orbit. Orbit in the sense the angular frequency that would describe an hypothetical complete orbit along these magnetic field lines of the electron. So the corresponding, of course, just moving from angular to frequency is just a factor of 2 pi. So this is the frequency of the rotation along this imaginary large orbit, okay, depending on the curvature radius. But on the other side, you see, you have an ultra-relativistic electron. So the velocity is just c, close to c, we can approximate as c. You know the velocity. Imagine you have a particle moving on a circle. You know the velocity. You know the radius, rho. So you immediately work out the frequency. So the frequency is omega, the velocity is omega rho, or omega is just 2 pi nu orbital. So nu orbital, you know the velocity, you know, or if you want, you know the velocity, you know the length of the orbit, and this is just 1 over the other is just the time it takes for one orbit, but 1 over the period is just frequency. You can look at this many different ways. It's very easy, and the two have to be equal, of course. So by equating the two, you immediately end up with the value that the fictitious magnetic field has to have in order to give you the acceleration that you want. So you immediately see that indeed the magnetic field, the fictitious magnetic field, is something like that. So once you know the Lorentz factor of the electron, once you know the curvature radius of the magnetic field lines, you automatically can work out. Now, you know this, you can exploit everything. In particular, you know that you can exploit, you can calculate the corresponding critical frequency. In this case, the critical frequency of curvature radiation, because now you are imagining that you are indeed in the presence of synchrotron radiation due to this fictitious magnetic field, because indeed this fictitious magnetic field is responsible, in your picture, is responsible for the acceleration that indeed you measure. Indeed, you know that the acceleration is due to different causes, but you imagine the acceleration of the electron is due to this fictitious magnetic field, which now you calculated to make, and which this precise value that we come up with is just the value that you would get to have that specific acceleration. So you can exploit everything. So for example, you know that most of the radiation will be emitted at this critical frequency, where of course the corresponding gyration is just what we call the orbital frequency, just like that. So just replacing, in particular, here, new orbit in this case here, you see that you end up with this formula. And this is very important to note. There's one big difference with respect to synchrotron frequency. You see, the curvature radius rho is something which is independent on the Lorentz factor of the electron, because it's something which is entirely due to the curvature of the magnetic field lines. So it has nothing to do with the electron. You can have whatever electron you want. The curvature radius has nothing to do with the particles that you put in there. But that means that the curvature radius doesn't depend on gamma. So it means that the scaling of the critical frequency in the case of curvature radiation is with gamma cube. Now, if you have in mind the corresponding critical frequency of the synchrotron, you will see that you have a different dependence, a different scaling with gamma. So here the scaling on gamma is more sensitive, is stronger. And you can, if you are somehow puzzled by this, look at this formula here. In the case of synchrotron radiation, because the curvature is due to the Lorentz factor, and the Lorentz factor also determines not only the gyration frequency, but also the curvature radius. If you work out something that we didn't do, but if you work out the curvature of the orbit for the synchrotron case, you see that the larger gamma, the correspondingly larger the curvature radius. If you fix the magnetic field and you increase gamma, you double gamma, also the curvature radius will double. Why? Because, well, the velocity is always c. You are dealing with relativistic electrons, but if you remember, the gyration frequency scales as 1 over gamma. So the period increases. The velocity is the same. The period increases with gamma, so it means that the radius increases with gamma. So when in the case of synchrotron radiation, gamma scales with, rho, the curvature radius, scales with gamma. That's why you end up with a gamma square dependence of the critical frequency. In this case, rho, the curvature radius, has nothing to do with the particle. All the particles have the same curvature radius, regardless of their Lorentz factor. So that's why you end up with a different dependence. And if you replace the values, here I just to show you an example, the typical values, the typical orders of magnitude for the curvature radius when you think of a neutron star is comparable with the size of a neutron star itself. You probably know that neutron stars have radii of the order of 10 kilometers, so 10 to 6 centimeters. So the curvature radius is comparable, of the order of. So if you just use here, you end up with these typical values, which immediately tells you that, for example, for when this guy is more or less 1, you see that the strong dependence on gamma can let you have radiation emitted at very different frequencies, and we will see a few examples of that. And so we can also exploit the total power. Of course we can. Beautiful. But again, you see, in this case, the perpendicular, so of course we are dealing with ultra-relativistic electrons, so you have to use the ultra-relativistic formula for the of Lamo, and again, the only component that you have the acceleration with respect to velocity is just a perpendicular. Again, we are in the case of an acceleration which is entirely perpendicular to the velocity. So this is the only term that survives. And again, if you replace the acceleration, just basic physics, you already know for many years, the acceleration is the velocity squared over the curvature radius, just like that. And this is squared, so you have to square all this guy. But you see, and this is the formula you come up with. So you just have this dependence. But let's focus. So again, the dependence squared with the charge, 1 over curvature radius squared. But look, again, another big difference with respect to the synchrotron case. In the synchrotron case, you had something that I encourage you to remember. The scaling of the power of the synchrotron power with gamma is gamma squared. Here is much stronger, gamma fourth. Why? Again, for the very same reason. If you look at this formula here, or better here if you want, in the case of synchrotron radiation, as I said, the curvature radius is proportional to gamma. So this guy in the synchrotron case is proportional to 1 over gamma squared. Gamma to the fourth over 1 over gamma squared, that's where gamma squared comes from. But you indeed, again, for the very same reason, here the curvature radius is the same for all electrons, regardless of their Lorentz factor. The power just scales as gamma to the fourth power. So you see, we exploited the knowledge that we acquired in the case of synchrotron emission just by changing the only thing that we had to change, and we derived both quantities. So the frequencies at which most of the radiation will be emitted, so the critical frequency in this case of curvature radiation, so scaling with gamma cube, and the total power with gamma to the fourth. Now, if we wonder what's the typical critical frequency as a function of gamma, well, let's, as I said, here there's just a plot of this function here. If you take this function here, and you have, the only thing you have to do is just fix a value of rho, of the curvature radius. And indeed, I told you, if you think of a neutron star, the typical value is just 10 kilometer. So by fixing 10 kilometer, this is just a function of a power law. Gamma scales with, new critical, so what I show here in the y-axis, as a function of gamma. And you see here, I just show you the different, I put the name of the different domains of the electromagnetic spectrum. So of course, this is just, this is not a strict separation between this. Is just, you have to imagine something which is smoothed out into the next part. But let's have a look. It means that how is to be interpreted this graph? Well, if you have a Lorentz factor, if you have an electron whose Lorentz factor is, for example, 1000, it means that for an object like this guy here, so for a neutron star with a curvature radius of the order of 10 kilometers, an electron like that will emit in the infrared at this critical frequency. Here I also put the energy of the photon in units of electron volt here in Earth of the corresponding. But again, you see, if you have very high, for example, 1 million, Lorentz factor 1 million, you can go up to the gamma rays. So you can span, depending just on the Lorentz factor of the electron, you can span from the radio all the way up to gamma rays. And that's indeed what we observe in the so-called lighthouse effect of pulsars. When the pulsar, you imagine the pulsar is spinning with the magnetic field axis, which is not aligned, which is has a different orientation with respect to the rotation axis. So when in the very moment in which the magnetic axis is pointing towards you, you will see radiation. And what you see is just a pulse of curvature radiation. And indeed, we see, since the region close to the close to the surface of a neutron star there can be huge electric field for many reasons. So you have a region in which electrons can be accelerated to extremely high energies. So indeed, you can have extremely energetic electrons. So depending on the energy of the electron, you see that you can have just a pulse of radio in the radio band, or infrared, UV, X-ray, gamma ray. And indeed, we know pulsars because of the lighthouse effect of their radiation. They are pulses, and they pulse every time the magnetic axis points toward us. So this is also a very effective way to measure their spin period. And indeed, as I said, we know radio pulsars, gamma ray pulsars. What we observe is curvature radiation. So getting back to the figure, to the previous figure here, this one, here, you see the acceleration is this way. The velocity is pointing this way. So because of the relativistic beaming, the radiation will be mostly emitted along this axis. And that's indeed what you see. Whenever, imagine this, you see this is the spin axis, the rotation axis. Whenever this guy is such that the magnetic field points towards you, you see a flash of curvature radiation. Now you know what it is. And you also see why you can have photons of many different frequencies, depending on the Lorentz factor. As I said, it has to be bright enough. So the possibility of having a coherent emission is just due to what I was telling you. If you have a bunch of particles, so whose size is negligible with respect to the wavelength, and this is a condition which is has to be fulfilled in order for the electric field to be summed up in phase. So as a matter of fact, let's have a look at what happens when you have n particles which are emitting not coherently. So every particle works on its own. So the resulting electric field will be unrelated with the electric field due to the other particles. So the total power that you observe is just n times the power of one single particle. We've seen that, of course, the power of one single particle scales with acceleration square. The acceleration is the same for all the particles, if you think, because of that. Then there is the gamma to the fourth power, which makes the difference. But the acceleration itself, from a kinematic point of view, is the same in this case, because they all have the same velocity and all have the same curvature radius. So essentially, you have the total power is just the sum n times the power of one single particle. But in this case, you see, the fact that they emit coherently, it's equivalent from a point of view of the resulting electric field to having one single charge. So with the resulting charge of nq, given the square dependence, it means that in this case, if you compare to the uncoherent emission, you gain an extra factor of n. So n particles which radiating coherently is not just n times more radiating than just one single particle, but n squared times. So that explains why this flashes of coherent curvature radiation can be bright enough to be seen. And indeed, as I said, that's indeed the case. Another very important property of coherent curvature radiation compared with synchrotron is that, if you remember, when we worked out the limits of synchrotron emission, if you remember, I told you, okay, for a given magnetic field, in order for an electron, that the energy lost in one orbit is negligible with respect to the total energy of the electron. You can have a limit on for a given magnetic field, you have a maximum Lorentz factor, beyond which the approximation doesn't hold anymore, beyond which the electron loses its energy too dramatically. The approximation of just gradual energy loss is no more applicable. But if you remember the numbers, you can get back to the slide that we saw last time. You see, for example, in the presence of a magnetic field of 10 to 12 Gauss, it means that if you consider an electron can emit synchrotron radiation in a non-catastrophic way, only if gamma is below 40. I remember this value. So some kind of 20 MeV, something like that. If you work out the same with curvature radiation, you see that in proportion, curvature radiation you can have, in order to avoid the catastrophic energy loss in the case of curvature synchrotron, in the case of coherent curvature radiation, you can have much more energetic electrons. For example, here there is an example. If you just apply the formula we've seen in the previous slide. So, for example, one TeV electron, so hugely 10 to 12 electron, so all much higher than the 10 to 7 electron that was the limiting case in the previous example for this kind of magnetic field. So I'm still using as an example this 10 to 12 Gauss. It means that if you consider a typical curvature radius of 10 to 6 centimeter, the frequency, the critical frequency of the curvature emission, you can easily calculate, or you can easily see from the previous. So 10 to 12 means 10 to 12 electron volts means kind of 10 to 6 something to here. So the electron has a Lorentz factor here. So you see that indeed you are in the very energetic gamma rays. Okay, 6 to 10 to 22 Hertz. So an electron, which is, no, this is the energy of the photon, sorry. So it means that, is this catastrophic? No way, because in this case, even when the electron is emitting such hard gamma rays, in this case, it takes it can afford 4,000 of these photons before losing its total energy. So it means that you can have curvature radiation at much higher, at much more relativistic, much more energetic electrons than for a given magnetic field, like in this case, than the corresponding synchrotron emission. Such an electron, such a comparably energetic electron in the presence of this magnetic field with a pitch angle much different from zero would catastrophically lose its energy immediately without even making one. So this is also very important. That shows you that can survive for much longer. So can indeed be responsible for the emission at such high energies in the case of when the curvature emission is dominant with respect to synchrotron emission. And that's it. That's all for the class today. So on Wednesday we will go through a completely different processes. We will be studying photoelectric absorption and also Compton scattering. Any questions?
Well, I will have a question, but on a precedent argument.
Yes.
I was rewatching the black body radiation, and we saw that the peak